I'm just quickly going over several consequences of this punctual eigenduality. First of all, we have a strengthened version of the Fourier inversion theorem. So if I have something that's in L1 and suppose its Fourier transform is also in L1, then I can basically recover the F by doing the Fourier transform of the Fourier transform. So this can be seen as a second version of this original Fourier transform. In the first version, we require F to be in B1, but now we don't have that assumption as long as your F hat is in L1, so you can do the Fourier transform again. Then you transform twice, but then you evaluate X inverse, you get your F of X back. All right, so the proof is fairly simple. So if you have consider this F of I, which is just equals to the usual Fourier transform, you have F of X, phi X conjugate dx. Okay, one way of doing that is if you just pretend this is phi evaluate at X inverse dx. And if you think about that way, well, this is just equals to, because your group is abelian, so you can replace the X inverse by X without paying any penalty. The modular function is constant 1. So this is phi X of X inverse dx, okay? So automatically, what do you have that because your F is in L1, so this one is in M of G, So what you have is that you're integrating something against F of G, M of G. So you have your F hat is inside B1. Okay, so the F hat is inside B1 of G. So this is, I should say, this is integrate against M of G, but by punctual eigenduality, you identify that as the M of G double hat. So this is the integral over the du of the G hat. Okay, so this one is inside B1. So because it's inside B1, so now you can apply the Fourier inversion theorem. So this is equals to the integral of you integrate over the double hat, and you know the double hat all has this form of X hat of something. So you just pretend that's what's inside the double du. Okay, so you integrate some X hat evaluate your phi, and then you do the F double hat evaluate at this X hat. Okay, so this is the Fourier inversion theorem. And let's just rewrite everything back to G, because the punctual eigenduality says dx and dx hat, they're the same. G and G double hat are the same. And this X hat of phi is the phi evaluate at X. And you have this F double hat of X hat, okay? Or you can pretend it's just a function of X. So let's just take out the X hat here. All right, so this one is basically the F hat of the Fourier transform of the F hat. So on the other hand, let me just copy down what we have before. So let me copy that line. So this is the integral of the phi x, F of X inverse dx. So essentially your F hat can be written as an integral in two different ways. And well, you know, this one has basically these two measures has to match. In other words, we have that the F double hat evaluated at X hat, that has to equals to the F X inverse, okay? So basically, well, I finished the proof. And just want to point out that, so if we want to, what does it mean is essentially if you want to compute the F of X, you can pretend it's the F of X double hat of the X inverse hat, which is just equals to, by definition, this is equals to the F hat of phi, and then you do the X inverse hat of this phi, you do the conjugate, so this is the usual Fourier transform evaluate at this X inverse hat, and then you do the X inverse hat is essentially evaluate at the X inverse. So what you have is that this is equals to the integral of the F hat of phi, and then you do the phi of X inverse, the whole thing conjugate, that's just equals to phi x d phi. And that's just the inverse Fourier transform you're familiar with, okay? So we now have this version of the Fourier transform. And the second thing I want to show that is the following. So if you recall that if I have a row inside M of G hat, we define this inverse Fourier transform, basically phi row of X equals to the integral of all the characters d of phi. So this one is going to be injection, okay? So it's an injected map from M of G hat to all the continuously bounded functions on X. So, and in fact, I want to show that this one is going to be injective from on the level of the measure space on G as well. Okay, so if you consider the Fourier transform from the mu from M of G, so if I take a measure and I do its Fourier transform mu hat, well, we know that's a continuously bounded function on the G hat. So this one is actually also injective as well. Okay, so it looks like a dual version of the previous result. So, and in particular, if you restrict yourself to the L1 space, considered as a subspace of the M, so in fact, so moreover, if you say F, let's say map L1 of G to the C0 of the G hat, that's also injective. Okay, so that's just immediate consequence. All right, so to prove this, well, we have this M of G, so we know G is equals to this double dual space, so I pretend it's the G of double hat. So every measure on G, I can think about it as a measure on the double dual space. So if I define, say, phi of mu, if I evaluate at a character defined as the integral of over G double hat of all the X hat evaluate at this phi, and then I use the d of mu of x hat. Okay, so this one is just equals to the phi x hat of phi is just phi evaluate x d mu of x. Okay, so this is just the Fourier transform of this mu. So because this map from mu to this phi of mu is going to be injective, well, now the mu to the mu hat is also injective. Okay, so the Fourier transform of this mu is just equals to this phi of mu. Okay, so this is injective. All right, and and another as a corollary, we have that if I have mu inside the M of G, and suppose your mu hat is inside L1 of G hat, okay, then this mu has to come from some L1 function. Okay, so there exists some f inside L1 of G, so that d mu is equals to the f times dx. Okay, dx is the Harmonic measure. So as long as your Fourier transform is an L1 function, then it has to come from the Fourier transform of some L1 function, in fact. Okay. So let's prove this fact. Well, suppose you have this mu hat is an L1, so let's just write out the definition. So by the definition of Fourier transform, you have that this is equals to the phi of x bar, and then you have the d mu x. Okay, so this is integrate over G. And another way of writing this is that I pretend this is an integral over G double hat. So I write it as the G x hat evaluate at phi, the whole thing conjugate again, and then d mu I treat it as a measure on the double dual group. Okay. So in other words, this Fourier transform is now a integral of some character of and again some d mu on the G double hat. Okay, so that just implies this mu hat, because it's an integral of the character against some measure on the dual of the dual. This f hat is a b function. Okay, it's inside b of G. Well, we know it's inside L1 of G as well by the assumption, so this is inside B1 of G. Okay, so now we prove that the mu hat is a B1 function, so the standard Fourier inversion theorem applies. So I can consider its Fourier transform, evaluate at a character on of the G hat, which is I should have a hat in all of here. All right. So because the punctual eigenduality, this G double hat is the same as G, so I can pretend this as a function on X. So let's just call it f of X. So by definition, this is going to be the integral of the mu hat of phi, and then I have x hat evaluate at this phi. Should clear this up. So x hat, and then I do the conjugate, I integrate over phi. Okay, so this is integral over the G hat. And we know by the usual Fourier inversion theorem tells you that this one, because mu hat is in B1, this one, the f or mu double hat is going to be inside the L1 double hat, which is the same as the L1 of G. Okay, so I get another L1 function. Let's call it F. Okay, so by the Fourier inversion theorem, I can recover the mu hat by the following. So if I want to know what's the mu hat evaluate at a character phi, then I can just integrate the double hat evaluate at a character of the G hat, which is, let's say, X hat. And then I integrate this X hat evaluate at phi, and then I do dx hat. Everything here you can pretend as integral over G by the punctual eigenduality now. So the first one, the F double hat, I call it F of X. And the second one, this is just equals to the phi X dx, okay? So this one is, if I want to rewrite it, because on the other hand, this mu hat by definition, this is equals to the integral of the phi X bar d mu of X, okay? So if I want to put the phi X bar or phi X inverse there, let's use the inverse of the X because our group is abelian. I don't need to pay the modulo function. I have this is equal to phi X bar. And then I have fx dx, f bar x dx, okay? So this mu hat is, on one hand, is the Fourier transform of this measure mu, but on the other hand, it's also the Fourier transform of this L1 function times dx. And by the previous corollary, we know this Fourier transform from m of g to the bounded continuous function of g hat is injective. So these two measures have to be the same, okay? So the mu is given by f bar times dx. So here f bar is just f of x inverse, which is still inside L1, okay? So this one is inside L1. So let's finish the proof.